first off, let's talk about oscillations in general. There are different types of oscillatory motion. The idea is that any sort of oscillation, we're talking about motion that goes back and forth around an equilibrium point. And the coordinate system we're going to use in here, which really simplifies things, is that 0 is your equilibrium position. So whenever we're talking oscillatory motion in this class, make sure that you set 0 to be the equilibrium position. Now, it goes back and forth in a repeating pattern, and that means that there's a period. Period is it's the amount of time necessary to come back to the original point in the cycle. We can then define a frequency, which is going to be just 1 over the period. And we've already seen this for circular motion. So circular motion is actually related to oscillatory motion, and that again, you come back to the point you started. But in general, we're not going to be talking about strangely shaped oscillations. You could imagine this is some sort of triangle wave. We could have a square wave that goes up and down in little pulses. We could have lots of different shapes in here. But what we're going to be interested in is sinusoidal oscillations. So sinusoidal oscillations, we're going to again still have a period where that is the amount of time between a peak and a peak, or a trough and a trough, or 1 0 and not the next 0, because note that those are in different points, but this 0 and that 0. In all of these cases, you can define period. And once again, period is capital T. We could define frequency from that, or if you knew the frequency of your oscillations, you could in fact calculate period from it. Same equation, just rearranged. So one of the things that, again, when we're talking about this 0 is our equilibrium position in the middle, and we then have positive amplitude A, or our motion goes to negative A. So we define amplitude to be this 0 to A value, and it's symmetric. The distance it goes in the positive direction is the same distance it goes in the negative direction, and this whole thing is defined by sine. Note, what we plot is important. This is always in terms of time, not in terms of position. So we're not looking at something varying in space right now, we're just looking at it varying in time. If you've possibly studied waves before in different contexts, that might be different, but here note, we're always talking about time. So, we're going to focus in on this sinusoidal motion. And any type of sinusoidal oscillation, we're going to call simple harmonic motion, at least for right now. Later, we're going to make it more complicated, but let's start with the simplest case. There's going to be different types of physical situations that can be described by sinusoidal oscillations, and the situation we will start with is a mass on a spring. And this specifically says it's an air track, and the reason for that is that means that there is 0 friction. It's an isolated system. So the only force we need to worry about here is the spring force. There's no air resistance, no friction to worry about. You have your normal force and your gravitational forces, resulting in equilibrium in the y direction, so we really have one force to worry about. We are effectively using the particle model here. Right now, we don't need to worry about rigid body motion, so we can simplify our object down to a particle and then trace out how this object would be moving back and forth on a spring. Now, this is in a way a motion diagram in that each dot is representing an equal space and time from the previous one, and we're heading down the page, and then we can see position on the horizontal direction. So again, it's kind of a strange way to do a motion diagram. However, you can think of this kind of like a seismograph plotting a motion of the ground during an earthquake, that we're going sideways, tracing out what's happening in time. So you can see that it plots out a sine curve, but that some of these points are more closely spaced than others. And that gets back to the idea of velocity. Now again, keep in mind that this is position versus time, so you don't have two-dimensional motion. This is still only one-dimensional motion. And we then see that we have maximum distances from equilibrium. And again, keep in mind that the 0 position always needs to be equilibrium. So this distance here would be x equilibrium. So when we talk about masses on the spring, we always say, hey, what is the distance from equilibrium, delta x? And that in this case is equal to x if we've set this equilibrium position equal to 0. We see it go back and forth, traces out a sine curve. We see that it's always going the same distance in and out. So now let's try to work with this a little bit more. Instead of using a motion diagram, we're going to make a plot. Again, we have position versus time. It looks like cosine. Now this is not completely general. Later we're going to make this a little more general, but let's start by working with cosine. And the equation now that's describing this motion is amplitude A is out in front multiplied by cosine of now 2 pi times t. So t is our independent variable, x is our dependent variable in this situation, and we have period capital T. So this is telling you what the position of our mass on a spring is as a function of time. I am literally pulling this out of the air right now, saying that if this is what our plot looked like, and I'm claiming it does, that this looks awfully like cosine of something times t. And we're going to talk about the fact that this is equivalent to pi over capital T, period, to omega, which we've talked about as angular frequency, and now it's going to be a type of frequency. So we're kind of pulling this out of the air, but in a few videos we're going to talk about the math necessary to really show this rigorously. So now let's talk through a bunch of different variables that are actually equivalent. We've said that frequency is 1 over period. And we also know that omega, again, what we've used to call angular frequency when it was in terms of circular motion, can either be expressed as 2 pi over period or 2 pi times frequency. So we really have 3 different variables that all really relate to the exact same thing. How long does it take to get back to the original position, and or how often is that happening if you use frequency? So we can actually write 3 different equations that are all exactly the same thing versus using period, frequency, or again, angular frequency. It is really complicated here to talk about this frequency versus that frequency. And the other thing to notice is that the units are a little bit different. This is just 1 over seconds, which we also call hertz. This frequency is literally, right, 2 pi f, and so that means that the units here are going to be radians per second. So whenever we're talking about omega, the book talks a little bit about this, the fact that this isn't technically angle anymore, it's cycles. However, I'll still try to typically refer to this as angular frequency to make it clear that I don't mean that it is not in fact this f. So if I ever talk about frequency, I mean f, I don't mean omega. And part of the reason for that is whenever you're actually working in an experimental situation with this, f is typically the thing that you work with. So mathematically, omega is easier to work with because you just have fewer other numbers hanging out, but f is actually simpler. So remember that omega has different units. If you talk about omega in hertz, you're incorrect. So let's talk a little bit now about how we calculate velocity. So you know that velocity is the derivative of position with respect to time. Obviously in this case we don't have a constant velocity, so it would be incorrect to refer to velocity as change in position over time. You absolutely can't do that here because it's not constant. So we take the derivative here, cosine becomes negative sine, so make sure that this minus is here, this is really important. And the coefficient that's inside comes outside. The a that was our coefficient outside remains. So we can also refer to this as V max as our coefficient, because when we go to plot this, cosine, the derivative, becomes negative sine, but now the amplitude, if you will, in a mathematical sense, is just the maximum velocity. So we now have a maximum velocity multiplied by negative sine, and we see here that our maximum velocity is then related to the amplitude and the period. The other thing we can do is go in and look at acceleration, and this is something we'll come back to later. That is the first derivative of velocity, so you end up with, oops, this a needs to not be in here, it needs to be out here. Sorry about that mistake. you get back to a cosine, and again, I haven't shown a plot here, but this would be equal to a maximum acceleration multiplied by a negative cosine of your original form. So think about calculus when you're relating position to velocity to acceleration, and that's going from cosine to minus sine to minus cosine. Do not use your constant velocity or your constant acceleration equations here because your acceleration is not uniform.